Good morning to everyone. Okay, will proceed with the class. So today quickly I'll give you some hint about how with photoacoustic approach, how this sensor, which is we'll consider one of this example, which is cantilever, let's say beam, reacts and provides us the output. Of course, we got the idea that it is basically deflection, which is deflection of the cantilever beam under the photoacoustic pressure or the force which is coming in, is inducing this movement, and what is the amount of that force, etc., and based on the modulating frequency, how it how this cantilever beam reacts. We will try to see with some equations, so that we will get idea that how mathematically it is expressed. So in case of a cantilever beam, a simple cantilever beam, under the application of a sinusoidal input, some force. So it is, let us say, f0 cosine omega t, where it is this is nothing but an external force or a pressure force, external force, which is generated due to the photoacoustic effect, and omega is nothing but modulating frequency, okay. And this modulating frequency is corresponding to the input source modulating frequency. The laser beam what we are using with a particular modulating frequency, and that is it determines this, assuming that the pulse width of the laser which is going to induce is much shorter, okay. And that is why, and this cantilever beam has a corresponding depending upon its beam characteristic length, okay, thickness, okay, the width of this cantilever beam, width, etc., determines its flexural characteristics. So the spring constant, okay, for this cantilever beam, okay, spring constant for this cantilever beam, okay, K is and can be related, is can be related to mass into its resonance frequency. This omega 0 is the first is the resonance frequency of this cantilever beam, okay. It can be determined using our beam theory, cantilever beam. I am not going into those details, but this can be, and this omega 0 is the resonance frequency of the cantilever beam, okay. Maybe in our case we will consider the first, the first resonance. Let us say first resonance, no overtones, we are considering the first fundamental, fundamental mode we consider, the resonance frequency of course 2 pi into f, correct, of the angular, it is angular rather frequency of the cantilever beam of the beam, and this is, if you do the calculation, which we are not doing in this case, it is available elsewhere. It is given by this, where E is Young's modulus for depending upon the material, if we are using silicon, so corresponding Young's modulus value, that silicon is taken, rho is density, L is the length of this cantilever beam L, T is the thickness will determine the first fundamental mode, okay, and the amplitude of this vibration. Of course, cantilever beam under this sinusoidal right force, the governing equation, okay, it is nothing but an harmonic oscillator, okay, in this case, right, it is nothing but an harmonic oscillator. So, right, considering this, right, considering harmonic oscillator, considering harmonic oscillator approach, okay. So, we are considering that this cantilever beam acts as an harmonic oscillator. The governing equation is right, given by this second order differential equation, okay. And from means this is mass, right, of this cantilever beam, this is corresponding acceleration. Of course, we will not be knowing this value, we can derive based on right, bending stress strain estimates, we can derive this acceleration value, but this is basically acceleration induced, right, and this due to the external applied force. B is the damping constant, right, K is the spring constant, okay, this external force. So, based on this differential equation and right, using boundary conditions, we can derive the amplitude of this oscillation as okay, we can derive like this basically. And in case, right, where the our modulating frequency, laser modulating frequency omega, if it is much smaller than the omega 0, what is omega 0? It corresponds to the cantilever beams, right, resonance frequency, is not it? If this is much lesser than 0, we can approximate this, right, a x omega, if right a this omega, which is a represents amplitude of this, right, vibration. So, in terms of displacement, we can say amplitude can be represented by f 0 by m omega 0 square, okay, approximately. Since omega 0 minus omega square is much right, omega is less than omega 0, and omega 0 square minus omega, sorry, over here that will be square value, okay, sorry, okay, square is much greater than p by m square, right. When omega is much smaller than omega 0, then this can be, and if omega is much greater than the resonance frequency, then x omega can be given by square, okay, it is given by this, okay, these are the two aspects. So, now how this, right, photoacoustic signal, right, comes into picture, okay. So, that is what we will try to see how this photoacoustic signal comes into picture. Now, if we consider let us see. Okay, let us say light source. Okay, right, light source with intensity, right, I lambda, right, passes through, and of course time dependent, it is a pulse, right. So, maybe I should express it in terms of NT pulse, right, pulsed input passes through, right, maybe of cell where absorption comes into picture, okay, and so right, some transmission will be there, but at present we are not worried about the transmitted light intensity, right. We are considering the absorbed intensity, and that absorbed intensity is basically responsible for heat, right, for the heat which is generated in this. Okay. So, yesterday I told you the heat is generated because of the transitions which comes into picture, and because of the transitions, vibrational transitions, vibrational rotational transitions will end up with during molecular collisions with other molecules will end up with energy transfer and increase in kinetic energy. So, this right, heat generation can be represented in terms of maybe right, is given by, okay, approximately given by P x, let us say, or P 0 into path length, right, into path length, let us say in this case d, okay, sorry, so x 1 minute, this p sorry, 1 minute, d, this is path length into the pressure or the input power, okay, and it is modulated input power. Okay. So, now here what it means, dq by dt represents, right, basically the heat which is generated, okay, and with respect to time, how it varies with time, which is generated depends upon absorption coefficient, okay, molecular absorption, correct, absorption coefficient. Px is nothing but the partial pressure of that, right, of those molecular partial pressure, okay, right, and d represents length of the cell, right. If I am using let us say intensity goes this right, transmitted, if there is a reflector here and I have a gas cell, sorry, with length d here, and if it is right coming with an angle theta, input theta, then and if there is a to and fro, right, but the intensity the light passes through this cell, gets reflected back through this cell, then the path length will be 2d divided by cosine theta, okay, right, depending upon this angle. It improves the absorption, of course, but in this case if it is a single pass, it will be into d, right. If it is double pass with some angle, very small angle theta, so that the light goes through, right, passes through this and returns back, right. So, the right, accordingly the path length increases, so that can be represented by this. So, in this case, right, so d will be 2d divided by cosine theta, but this is the amount of heat which is, right, generated, okay. So, that can be given by this form. Now, this heat is basically generated is basically responsible for the pressure, right, variation, etc. And that relationship can be given by P V is equal to nRT, where it is a right ideal gas equations, right, where n is number of moles, R is gas constant, T is the temperature, P is the pressure, V is volume, right, in this cell. So, we can represent it by right by P plus dV by V is equal to dt by T, okay, based on the differentiation. And right. So, change in temperature from the first law of thermodynamics, no, we can right, we can derive this way, and change in temperature can be right captured based on the first law of thermodynamics as right change external work internal energy change right plus external right work done, which is equal to let us say n CV dt plus P dV. Okay. So, this is the first law of thermodynamics, which gives the relationship between change in internal energy, work done, external work done, and that is related with the right heat input output, right, and it can also be represented by change in internal energy by NCV dt plus external work done is P dV, etc. Okay. What is N? Number of moles, and what is CV? It is a molar capacity at constant volume. Okay. So, basically specific indirectly it is nothing but the specific heat, okay, at constant volume. Okay. So, what happens? Let us say I do not care about the external work done, and if there is an heating effect coming into picture, if I if there is an heating source, then that will get converted into internal energy, right, change in the internal energy if there is no external work done. So, what is internal energy is nothing but the mass into specific heat into temperature change. Okay. So, mass into specific heat into increase in decrease in temperature. Let us say we heat the water, right, we input internal energy, we put external heat, it gets converted into rise in the temperature, isn't it, and that can be estimated based on by neglecting other aspects, thermal conductivity, external work done, if we do not consider, it is related to internal energy change increase. So, if we know the mass, we know the specific heat, we can estimate approximate temperature increase. Okay. So, that is related to the first part of this right equation. So, this and P work done by the gas is given by P dV. Okay. So, this is the one representation, and then using this two equations, okay, this equation and this equation, we can get right by substituting the values of this equations, we can get as dP by P is equal to gamma plus gamma dV by V equal to gamma 1 dQ by PV, where gamma is Cp by Cv, which is equal to gamma into R upon gamma minus 1 divided by R upon gamma minus 1. Okay. Okay, this is the way. So, we simplify, we use these two equations, okay, this two equations, and try to derive this right representation. Okay. Now, dP is related to in a volume change cell. Okay, it is also related to k dx by a. Okay, and so k is nothing but the right string, it is known as string constant. Okay, or spring constant in case of a cantilever beam. A is the area, okay, and a cantilever beam dx is the end displacement. Okay, so and dv is equal to half a into dx. Okay, so these two changes, right, because of the pressure which is generated, the cantilever beam will experience some displacement, isn't it? So force into, so that is represented right by this form. Okay, so basically change in pressure into area is equal to the force which is acting on the cantilever beam, and considering spring constant of the cantilever beam as k into displacement will give us the force, right, indirectly. So that is the relationship, and volume change will also come into picture. So these two parameters if we consider and substitute these two forms again in the previous equation, that is dp by p is equal to plus gamma dv by v is equal to this. In that if we substitute, then it becomes k upon a into p plus gamma a upon 2 v to dx is equal to gamma minus 1 dq by pv. Okay, or k plus gamma a square upon 2 v dx is equal to a times gamma minus 1 dq upon v, which is nothing but df. Okay, and so delta f is a into gamma minus 1 dq divided by v. Okay, and so divided by v, and integrating over the time we can also, right, estimate, right, the force which is v and we know what is dq by dt, that is the basically based on the heat which is generated due to the absorption by the molecules, right. We already know this form, so we can substitute this aspect over here. So delta f can be represented by a minus 1 by v alpha x p x into d to p 0 to 1 omega sine omega t. Okay, so this is, so right, so that is the total force which is integrated over time dt, right, will be captured, and amplitude of this maximum, that is maximum, right, value where sine omega t is, right, 1. So f 0 amplitude of the force, amplitude, okay, right, force f 0 can be given by gamma 1 by v alpha x p x to d p 0, right, divided by omega. Okay, so this is the force which is given this. Okay. Okay, and so you can as if you go back, we had derived depending upon the omega value, right. If omega is less than, right, omega 0, accordingly, right, we can estimate the amplitude a x, right, at omega, which is f 0 by m omega 0 square, which we had mentioned in the previous this thing. So, here f 0 can be substituted. So, right, the signal amplitude in terms of displacement, right, can also be captured. Okay. And this displacement can be correlated with our detector signal. Okay. So, indirectly we can see this, that the displacement is proportional to the absorption parameter, it is proportional to the input power intensity of the light and how much it is getting absorbed. It is proportional to the partial pressure, so the concentration of this, right, gas at sector molecules. So, we can see that acoustic signal, whatever intensity we capture in terms of photoacoustic signal or in terms of corresponding displacement of the cantilever beam, it is proportional to the concentration of the molecules present or absorption coefficient or intensity. Even if we increase the intensity of the light, the acoustic signal will also enhance, okay, for the same concentration. Right. But in order to measure the concentration, we will be keeping the all other parameters fixed, and we will try to see what is the signal variation in terms of displacement, in terms of photoacoustic signal based on the change in the concentration. All other parameters keeping constant, right. So, D will be constant, P 0, omega, everything is constant, same. Okay. What is varying? Absorption coefficient is also constant. What is varying is Px, concentration, partial pressure, right. Then it can give us the idea. So, this gives us the right approach of detecting the concentration of gas molecules using this, right, approach. So, this is nothing but the photoacoustic approach. Just to give you some idea. So, okay, one. So, this you can see if there is a light input, the corresponding over, maybe let me describe. So, light infrared light is going through like this through the cell, it reflects back here. Okay. So, this cell which consists of the, let us say, certain trace gas absorbs this infrared light, the pressure, the heat is generated, which indirectly changes the pressure and the volume, right, and this changes are being captured using this cantilever beam deflection. This deflection is captured using interferometry approach. Okay. In this case, okay, it can also be captured using diaphragm type capacitor microphone also. Okay. Right, it can also be captured this part by based on the bending stress induced in cantilever beam. However, for a very small such detection, this interferometry approach is very sensitive phase change. So, we can capture this information which indirectly connects with the concentration change, right. Now, we in our lab also we have some such experiments we have conducted, okay, and we have found for various such gases what is the right concentration values, right. So, maybe okay. So, so for example, we change this is just to give you an idea, you do not have to remember, but we change the concentration of CO2, right. X axis is concentration of CO2, y axis is the photoacoustic signal. Here we captured the photoacoustic signal using a photoacoustic cell, PA cell, and microphone, okay. Not the cantilever beam, but we use a microphone, okay, capacitor based sensing microphone to detect the acoustic signal when the input light with the wavelength matching with the CO2 absorption molecules, which is the wavelengths what we used where of course different bands, okay, absorption bands. In this case 2017 nanometer band or 2000 around 2000 nanometer band. When we use that, we can see the absorption by the CO2 molecules, and accordingly based on the change in the concentration of the CO2 molecules, the photoacoustic signal is changing. Okay, and it is changing linearly, as I told you, it is linearly, right, proportional to the concentration, okay, or partial pressure of this. Same is the case with ammonia and CO. Only thing is, see, ammonia has also absorption band around 2017 nanometer. CO2 also has absorption bands. So, when we want to capture the mixture of these two gases, indirectly we are capturing a photoacoustic signal which is the sum of both of this, right, signals. So, we should be how to find out each individual concentration is, we will have to use differential approach. Differential approach means either we will have to use two different wavelengths and capture photoacoustic signal for both ammonia and CO2 together for two different wavelengths, and then we can derive the concentration difference, right, because you know that from our all these derivations, right, in short, this whatever I derived, basically the photoacoustic signal, okay, PA signal, maybe displacement, maybe output voltage in terms of microphone capacitor is proportional to some constant, okay, some cell constant, some quality factor of that design of the cell, and etc., and proportional to input power the line, as well as alpha value, absorption right coefficient, or indirectly maybe a sigma value, right. A sigma is absorption coefficient, and distance also, and concentration. Okay. So, this is concentration and concentration, okay, of the molecule present, right. So, basically right, we will include all other parameters related to cell, related to absorption, not absorption but other parameters, everything in this, right, C cell into Q, but it is proportional to this. Now, from this equation we are clear that PA signal is not proportional, I can represent it by equal also, right, equal to some constant, okay, into sigma lambda into n, correct. All other parameters are constant, okay, constant parameter, right. So, so if there are multiple molecules of different this thing, we need multiple wavelengths to solve this equation, isn't it, right. For each particular wavelength, sigma for corresponding those molecules will be known to us. So, concentration can be estimated, right, for individual. So, it is a very simple, right, approach in order to capture this information about concentration change, etc. So, that has been done, that is what we wanted to show. Now, there is one more approach as a sensor based approach, is to use tuning fork. See, what we were discussing about cantilever beam, right. Now, we can also use a tuning fork, okay, a tuning fork, and capture. So, let us say this is the tuning fork, okay, this is the tuning, okay, this, and let us say this is placed within the gas cell. So, let us say this is a gas cell, and I should okay, tuning fork is placed within this guest cell, okay, transverse, of course the picture is not very clear, but transverse. So, the molecules are all present over here, and when light passes through this, what will happen, the molecules which are here, and when light interacts with this will produce acoustic, right, a photoacoustic signal, and that photoacoustic signal will produce pressure waves, this pressure waves, and hence the tuning fork will start vibrating. And so, based on this, the tuning fork amplitude, right, can help us, displacement basically amplitude can help us to determine the photoacoustic signal strength. The advantage with this approach is we can remove the influence of the external force. Okay. See, if the external pressure waves are coming from outside, will deflect the tuning fork in a different way, right. So, if external force is, let us say, right, if this is the tuning fork, and if external force acoustic waves coming from outside, the deflection is going to be, right, of course this is little, right, but it will be like this. But if it is the gaseous molecules which we want to measure, right, they are going to generate external force. So, the tuning fork deflection, right, will be like this, or oscillations will end up with, right, different, right, this, right, tuning fork oscillation. So, which is symmetric, right, which is different, and that can help us to remove the external such acoustic signal, and at the same time measure very small. And this tuning forks are made up of quartz, similar to the quartz watch, okay, very small size, millimeter, few millimeters length, etc. And they can be placed. So, the price of this tuning fork is very less, right, few dollars, right, or few hundred, not even 100 rupees, less than that. That small tuning fork, and with the help of strain gauge approach, we can capture the signal very easily. This, okay, and it is known as quartz enhance. Okay, QE, quartz enhance, QE pass, photoacoustic spectroscopy technique. Okay. So, quartz tuning fork is used to enhance the signal. Is it okay? So, this is another way of improving. So, this system can be very compact, very small, and it can be used to capture the signal, photoacoustic signal, right, using, right. So, it is just molecular, right, signatures are captured with the help of tuning fork, and you can, this picture we have taken from the Thor lab, right. So, now it is possible to fabricate such simple, right, gas cell with a tuning fork placed within this. So, the gas cell will allow gas input, output, measurements, everything is done, and light input, but the size, beam size will be limited to the, right, the separation between two forks, right, in this tuning forks. Okay. That is okay. So, that is the way that we can capture. Now, right, you could understand that how absorption, it is also absorption technique, but we are capturing the information in terms of photoacoustic signal. So, why in biophotonics this photoacoustic signal becomes much more important, because of the losses, the scattering which comes into picture when we are considering, let us say this was only a gaseous, right, medium. So, not much of scattering other than the absorption was is observed, but if we are considering tissue samples, okay, tissue samples which has right, different, let us say, layers, different tissues. Now, if light is trying to propagate through this and we try to capture the information in terms of absorption through the tissue or reflection also back through the tissue, it becomes much difficult, because the scattering is so large that the light intensity diminishes, right, as we try to capture. So, signal to noise ratio becomes a very challenging factor. Okay. And you could observe, you pass the red color light through our finger also, you will see that the even if it is 1 millimeter diameter laser beam, when it passes through this, you will not see the transmitted light beam as exactly, right, 1 millimeter diameter. It is all scattered light that you will see all around. So, that is you will be able to observe that because of the light scattering. So, however, the advantage with this right photo photo absorption is you can selectively pick up the species of interest. Okay. So, light is very much desirable in order to measure certain species or characteristics of the species. However, the signal what is generated either in terms of transmission or reflection, absorption, etc., is very difficult to capture. Okay. When we are interacting in presence of lots of tissues, surrounding tissues, etc., it becomes difficult. So, the technique which can be used in this case is photoacoustic, right, spectroscopy technique, of course, photoacoustic technique. So, we use light, okay, photons to generate temperature change, to induce the energy of or convert light energy into heat energy via absorption, and the modulating light source can produce acoustic signal and capture the acoustic signal, okay, using a transducer. Okay. So, instead of capturing the light intensity by the detector, we can capture acoustic signals, okay, which are generated right through, and acoustic signal scattering is much lesser when it passes through the tissue, okay, because of the characteristics of the right molecular, the impedance is quite less when it passes through the tissue. Okay. So, the acoustic signal is captured over here. Okay. So, if we capture this acoustic signal, it allows us to measure the presence of, okay, right, some or the characteristic of that particular tissue. Okay. So, what we are trying to capture is we pass the light beam and we capture the acoustic signal, and if I capture the acoustic signal from all different angles surrounding the tissue, I should be able to get the characteristic of those acoustic signals in different directions, right, generated, and maybe we may be able to derive the tissue characteristics from there. Okay. So, it can be converted into the tomographic, right, imaging modalities. So, maybe we will try to see that part, the tomorrow's right class. So, which has lots of applications as far as right biophotonics application is concerned, photoacoustic tomography. Okay. So, we will see how exactly this right approach is can be used for imaging modalities. Okay. Yeah. Thank you very much. Okay.